Should we start with question or should we get to the jump to the meat so that I don't lose half the lecture? Like, okay, let's try it. So, like, what have we done so far? So we have defined this. I've talked a little bit about Anosov representations. Of course, Anosov representation is a word, and one could talk for 3 semester courses about them and not finish up the material. And then I specialized to representation of fundamental groups of surfaces, and we have defined these theta positive representations. So, like, and so this is a representation rho from the fundamental group of a surface into a semisimple Lie group G, a very special semisimple Lie group G. So maybe one of the groups that were in my table down here yesterday that admits a theta positive structure, so that I can say that this representation is theta positive. So this meant that I have a family of diamonds in the flag space F theta associated to G, this boundary of G, encoded by this set of roots here. And these maps cyclically oriented entapoles to cyclically oriented entapoles. That was the idea. Like, these are special groups that admit this ordering that we encode in diamonds. And I told you that theta positive representations are exercise open if you believe that they are Anosov. And we talked yesterday about some geometric properties of this theta positive representation, that is this cross ratio being positive. And I was telling you that these will lead to closedness of this set in the character variety. Okay? So the main focus of my lecture today is to explain to you a theorem that we proved with the same set of co-authors, so Jonas Beyrer, Olivier Guichard, François Labourie, me, and Anna Wienhard, that says that is another geometric property of theta positive representations. Namely, if rho is theta positive, then I start from a topological thing in the surface. So I have my surface as G. And I choose 2 curves, gamma and beta, in the fundamental group of the surface, with the intersection of gamma and beta at least 1. So I stress that this is a topological assumption. So this means that I have one curve, maybe this one, and this is gamma. Like I chose any geodesic in any hyperbolic metric, and I chose any geodesic in any hyperbolic metric representing beta, and I want that they intersect. And I'm stressing that this really is a topological property. It's not something that you read in the, okay, if I have the fundamental group of a closed surface, as I'm having here in this setting, of course, the fundamental group remembers the surface, so you can read it from the group. But I could also do the same theory for free groups or surfaces, open surfaces, or even surfaces of infinite type, where just the free group doesn't remember if they intersect. But in order to know what it means that they intersect, and in order to talk about positivity, I need to choose an underlying surface. So it's a topological assumption on my 2 elements. And the second piece of information that I need is I choose a root alpha in theta, and then the associated weight omega alpha. So like I can think of omega alpha as the fundamental weight for alpha if you know what that is, or otherwise you can think of any linear representation of G as we were doing yesterday, where this is the log of the first eigenvalue, and the gap is log of the gap of the first 2 eigenvalues is alpha. And then what we prove is this inequality of the eigenvalue of these 2 elements in G, which is e to the alpha of lambda of rho of the first one, gamma, minus 1 times e to the omega alpha of lambda of rho of beta minus 1. This is bigger than 1. One way of reading this thing is you pick your favorite group, maybe the log of the eigenvalues of my element. And what this is saying is that I have some algebraic function of the eigenvalue of one element times some algebraic function of the eigenvalue of the other element that's bigger than 1. So maybe let me make it concrete in one example. In SO PQ, which I remind you had the positive structure for F1 P minus 1, the set of isotropic subspaces of all dimension but the last one. And this means that for any k smaller than P, I have that lambda e to the alpha. So denoting now by, this is bad, but let me call, I mean, I shouldn't have called lambda those, but let now lambda 1 up to lambda k, lambda p be of, someone can tell me a letter for the eigenvalues? Let's call them,
mu?
Yeah, mu we had as a Cartan projection. Another nu. Let nu 1 of G, nu p of G be the eigenvalue of G with modulus of nu I of G bigger or equal than 1. So like I have my any element G in SOPQ has at most P eigenvalues that are, I mean, it will have, its eigenvalues set is going to be nu 1 up to nu P, then I have a bunch of 1s, and then I have the inverses of those. This is because I'm in a group. And I'm counting them as generalized eigenvalues, and I'm counting them with multiplicities, so that I have exactly P here. And I order them so that the modulus of nu 1 is bigger or equal to the modulus of nu 2, which is bigger or equal to the modulus of nu P, which is bigger or equal than 1. And then what I'm saying here, e to the alpha of lambda of rho of gamma is going to be the absolute value of lambda k of rho of gamma over lambda k plus 1 of rho of gamma. This was nu, sorry. Minus 1. And this was absolute value here. And all minus 1 times the absolute value of nu 1 up to nu k of rho of gamma minus 1. And I actually need, I mean, I need a 2 here to be correct. This is bigger than 1. So this is like, this was to say that it's some combination of the eigenvalues, some formula involving combination of the eigenvalues. And why I find these formulas, so, and this is what we call the color lemma. And if there are no questions on the statement, I want to tell you why I find this inequality interesting. Maybe I want to tell you why is it a color lemma. I want to give you an idea on how this is useful to prove closeness. And then if I have time, I want to tell you a bit of how we prove this. Okay?
So do we need gamma to have self-intersection greater or equal to 1?
And no, so sorry. Here I needed. Thank you. I needed beta.
Okay, thanks.
And maybe something that's worth stressing is that I draw these as simple curves. That's not necessary. And I could take a curve with self-intersection and use it twice. That's something I could do. That's like that. But this is one picture that's helpful. Huh? Any more questions? Any more typos on the board?
Sorry. The modulus of V1 to Vp is greater than 1. Is the P the same of the SOPQ?
So P is P. And here I have, like, I'm in the standard convention that 2 is more or equal than P, which is more or equal than Q. And I had like the nu 1 up to nu p were the eigenvalues of modulus at least 1. So, and these are generalized eigenvalues. So I could have a complex eigenvalue of multiplicity 2, then I record it. And I could have a Jordan block that's long 7, and then I write 7 times the same element. Okay? So this gives me a way of having, I want to have p plus q generalized eigenvalues in total. And the p plus q generalized eigenvalues will be nu 1 up to nu p, their inverses, and a bunch of ones. Because in the center, because you are in the group, preserving this form means that you have a or bunch of guys of modulus 1. That's could have complex numbers of modulus 1. Those I don't care for these things. Yeah. Let's see first. Okay, let's observe a few things. In particular, an inequality like this is telling me that so nu k in absolute value is bigger or equal than nu k plus 1. But if this inequality holds, then it's strictly bigger, right? Because otherwise here I get a 0, and no matter what I multiply, I still get 0. That's not bigger than 1. Yeah? So observation, so like easy corollary is that for any gamma in gamma, alpha of lambda of rho of gamma is bigger than 0. Which means, maybe let me draw this, suggested this, which means that if I have, if this is a wall associated to alpha, then I don't have anything in here, right? I'm really away from this thing, from this wall. We were saying that this was our A plus, that was a strict fundamental domain, so a priori I'll have elements whose Jordan projection lands in here, but not in the image of a theta positive representation. This is for all alpha in theta. And maybe why is this a color lemma? This is a color lemma because not only I know that this is bigger than 0, but I know that if this is very small, if this is very close to 1, so this alpha is very small, then this is very close to 0, which means that this is very big, which means that the rest is long. And this is what's the color lemma in hyperbolic geometry. The color lemma in hyperbolic geometry, that I'll maybe draw adapted to what the picture there was, is that if in my hyperbolics, if now S has an hyperbolic structure, if I have a curve that's short, any short curve, like the curve gamma to be consistent, if gamma is very, very short, there are examples of hyperbolic structure with gamma very, very short. I told you with Fenk-Nielsen coordinate, you can choose any length for this guy, because I can build pair of pants for any length. But also from this pair of pants construction, you see that if gamma is very, very short, then it has a very, very long color neighborhood that's embedded in the surface. So this is roughly log of length of gamma. This is in the hyperbolic LH2 of gamma. Minus log. The length in H2 of gamma is very, very close to 0. And so I have the log is very, very big negative number, and minus is a very, very big number. And this means that if beta now crosses it, in order to cross it, it has to start somewhere, but has to travel all through the color and get back. And so it picks up this length. And this is roughly what we see here. Because what we see here is that if we think of this alpha as the hyperbolic length, as a way of measuring the hyperbolic length, if this is 0, like around 1, e to the alpha is roughly alpha. And so it means that e to the omega should be, so omega, which is some other way of measuring the length of the other element, needs to be long logarithmically. Yeah? So this is, so this like so that's why this is the color lemma. So similar if alpha of lambda of rho of gamma is very close, I mean, goes to 0, it's very close to 0, then omega alpha of lambda of rho of beta is roughly minus log of alpha, is at least, I mean, roughly at least of log alpha of lambda of rho of gamma. So everything that crosses it becomes long.
And this fails for general Anosov representations?
This fails for general Anosov representations, even in SL2C. In SL2C, you can find example in quasi-function manifolds in which you can choose two curves that intersect, and you can make one very short in the top of the manifold and one very short in the bottom of the manifold. So like you can like pinch two multi-curves that intersect non-trivially. That's, and for general Anosov representation, you can do everything that you want. Yeah? So this is somehow, I mean, one can think of this as a Margulis lemma kind of argument if you have the intersection point. This is because in the surface you have the intersection point, and we know that curves that intersect in the symmetric space, I mean isometries of a symmetric space that intersect somewhere cannot be simultaneously short if they generate a free group. This is a general fact of symmetric spaces. But this does not follow from that, because in the symmetric space, the places where this guy translates little can be very far away, because the symmetric space is very big dimensional. But still, the positivity encodes this linking in some way. Okay? Questions on this? Okay, so this is the statement. And like to me, this is very like, why should this be called higher rank Teichmüller theory? Because this is really a Teichmüller theory statement that holds for these kind of representations, and there's no reason to hold for other kinds of representation, even if they are very nice. Okay, so maybe it should be called higher rank Tarstone's theory of surfaces, but that's or Keen, whatever, Fricke spaces. But okay, any questions on this? Any comments? Any complaints? Okay, then let me tell you briefly. Like, I want to tell you a few words about the proof of this stuff, but maybe let me close the circle first, so that let me tell you first some ideas on why this is helpful to prove the theorem that theta positive representations are closed in the character variety. I'll cheat a lot here. So this is telling us that they form connected components. But the closedness statement doesn't really require that this surface is compact. You can do it for any kind of subgroup of PSL2R, where you have an ordering on the boundary at infinity. This gives you a notion of positivity, and the same idea will give you closeness in full generality. So how do we do this? So what's the why these two pieces? These are two. I mean, to me, I presented you two geometric features of theta positive representations, and I want to tell you how these two geometric features are useful to show closeness. And like just the idea, because I'll zip lots under the rug, and maybe like this sketch will not be. Is not really what we do. I mean, we do slightly different thing, but that's to keep some ideas in mind on how this could work or should work. So I have rho n. I want to show that this is closed. I have rho n theta positive that converge to rho, some representation in the character variety of which I know nothing. I mean, I know that's discrete and injective because we know that discrete and injective is a closed condition in the character variety. But that's all what we know, right? And then we first use the color lemma to say that for any gamma in gamma, alpha of lambda of rho of gamma is bigger than 0. Why? Because I had that inequality up there, right? That's like that corollary. No, actually the stronger version of the corollary is telling me that the length of, like, I can control the eigenvalue, the top eigenvalue of the limit, because the top eigenvalue of the limit is going to be, the eigenvalues are continuous on the character variety. And so these, knowing the eigenvalue in the limit will bound the roots of the intersecting curve. Because for every n big enough, alpha of lambda of rho n of gamma is controlled by omega of lambda of rho infinity of beta, something that crosses it, which is finite. It's finite because this representation exists, thus it has eigenvalues. And the eigenvalues like converge continuously over the character variety. Having this proximality tells me, it's okay? Makes sense? Having this proximality tells me that for any gamma and gamma, rho, so there exists, I can define phi, maybe phi, the bound, like I want to show that rho is positive, so I want to have a boundary map for this limiting representation. I'll call it phi. Phi is my boundary map that I'm trying to construct. I told you that in general, boundary maps don't exist. In general, the limit set is too complicated to admit such boundary maps. But I want to construct one and show that's positive. And having the fact that the roots are positive tells me that I can define phi of gamma plus and phi of gamma minus, and these are transverse. Having this eigenvalue gap, I mean, knowing that nu k is strictly bigger than nu k plus 1 tells me that I have a generalized eigenspace for the first k. And this is what the value of the boundary map is going to be. And the phi of the inverse is going to be the bottom ones, which is going to be transverse by construction. Yeah? So this tells me that I can define the value of the boundary map at all attractive points. That's a dense set in the circle. So this is boundary of gamma. So this is my gamma. This was gamma plus. This was gamma minus. And from this dense set that's everywhere, I can define it. And if I stick to one orbit, I get, this is going to be gamma invariant, gamma equivariant, this map. So the second step is to show that the positivity of the cross ratio of CR omega tells me that phi CR omega, this was the result that was discussing yesterday, tells me that phi n are Lipschitz in some suitable way, not quite, but like, I mean, like are Lipschitz as submanifolds, like are rectifiable as submanifolds of the flag space. I mean, they're not Lipschitz as map because I don't have any Lipschitz structure up here, but I have a smooth structure on the flag space, so I can say that these are Lipschitz submanifolds or like a rectifiable, like the image of phi n. Maybe I write it like this: phi n of the boundary of gamma inside the flag space for theta is rectifiable. And so I can make it up to subsequency, I can make it converge pointwise. And furthermore, so this is one first thing that positivity gives me. The second thing that positivity gives me, with quite some work, means that the limit is transverse. Maybe this, like the positivity of the cross ratio together with this seed of transversality lets me get transversality everywhere. So I get that I have this sequence of map, I extract a limit, I get a map, I mean, a pointwise limit, and this pointwise, I can make this pointwise limit agree with this value that I had here, and I can spread this seed of transversality to get that this is transverse everywhere. And then the fourth point is that then phi is theta positive by essentially the same the properties of diamonds. By the same arguments that I was hinting in the exercise to show that positive, that Anosov theta positive are open, because if I have a limit of positive map that's transverse, stays positive. By the exercise about openness, which is not quite part of the exercise sheet, but that's fine. That's life when you have a small baby. Make sense? So this is an idea on how these two geometric pieces, that one up there and the one we discussed yesterday, help towards proving closeness, if that's what you were looking for.
So in 3 you have to prove some uniform transversality to get that the limit is transverse.
Yeah, so somehow the idea in 3 is that you have transverse, like you use the positivity of the cross ratio to say that if I have I had my 2 transverse point, and that cross ratio positive implies transversality, because the way the cross ratio was defined essentially. If it's non-transverse, it has to be 0. And then you use the group action to put 2 transverse points inside, and this bounds the cross ratio, and this gives transversality. You have to play some arguments with the group action, the goodicity of the group action, to make pairs of transverse points inside any kind of interval. And that's the rough idea. But I mean, it's actually, in the paper we don't prove this, because there was a previous paper of Anna, Olivier, and Francois that proved in the Anosovness, proved this stuff, this step here with slightly different techniques. Where they were proving theta positivity, this gave these steps here once you have the seed of transversality given by the cross ratio and the positivity of the cross ratio. But yeah, so this is more like the approach that we take with Jonas in the previous paper. But this can be made to work with some tweaking it a little bit. More questions or comments?
Excuse me. What do you mean rectifiable?
Yeah, I mean that I have the flag space. It's a smooth manifold. So I can choose a metric on it. Yeah, I can choose a distance. That's it's a compact space. So you can any distances that are reasonable are comparable. And what I want is that this curve has this if you take smaller and smaller points. You can define the distance as length space. So meaning that if I take 2 points and I take the midpoint and I sum up these distances and I keep summing it, I get some finite number. Yeah? So that's so it's if it's a reasonable curve, even if it's not geodesic, I can start from 2 points. I can define the length of this curve between A and B as the supremum of take some sets in here, sum up all of these distances, and this is some approximate, this is the distance of some polygonal path approximating your curve. And if your curve is rectifiable, then no matter how fine this refinement is, you get always a finite number. That's the length of that curve. But if your curve was very fractal, or the Hausdorff dimension bigger than 1, then this does not converge. If you make it finer and finer, you explode. It gets arbitrarily long. And what you should have in mind is that for typical Anosov representations, the limit curve has bigger Hausdorff dimension than 1. So doing this procedure will explode. But these are very controlled. And they're are Lipschitz submanifold, or are have finite length in this setting.
Thank you.
Yeah? Yes?
Is the pointwise limit also, do you have to prove that it is rho invariant?
Yeah. because a priori we take subsequences and it's not clear. And in fact, like when we do it, we actually carry out this program this way with Jonas in the SOPQ case, and there we take a pointwise limit, and then we take right and left limits of the pointwise limit, and that becomes invariant. And then you show that it like does what it should at the point, but you need to like, I don't know. Our argument is not super neat. I mean, it's just like it's some work to make it really work, but you can make it work. Okay. More questions or comments? If not, I guess I have about 20, I mean, a little bit more than 20 minutes left. And let me tell you something about the proof of the color lemma. Yeah. So the proof of the color lemma is going to be a cross-ratio computation, essentially. And like it's built in cross ratios. And but one important problem is that we have a cross ratio on the boundary. Like we want to compute cross ratios on the boundary of the group and use some positivity of some tuples to get the result that we want. So like maybe let me just start drawing the, let me not leave it like that. So there are two problems. So we know a cross ratio that let us know what's the right and like the second term in the thing. So we know. So like,
sorry, can I ask?
Yeah, sure.
So can you generalize this color lemma to the cosplay so that you can generalize this result to groups? Or?
Yeah. This color lemma works for any positive representation of any group that has a cyclic ordering on its boundary in a reasonable way. So for any discrete subgroup of PSL2R, we have a notion of theta positivity, and this color lemma will work.
Okay, and also this theorem.
With and the closedness works the same. Like also like the positivity of cross ratio was really just for positive four tuples. So there's no group behind.
Closedness is okay, and for openness you need some assumption on the cost.
Right, exactly.
Okay, thank you.
Yes, and in general, like if you take I mean, geometrically finite group, like something that really has cusps, it's not going to be open, because like it's only going to be open in the set where you prescribe that you still have a fixed point on the cusp.
Yes.
Because like if your cusp is unipotent, you can always perturb it to make it elliptic and swap the levels. But
thank you.
But even for a funneled, surface, you say this still.
I mean, for a funneled surface, like if you like this like the point that for a funneled surface you can deform to be cusped within the character variety, and then you lose the openness at the cusp point. For a funneled surface, it's Anosov, so it's open and closed locally, but then at some point you will lose the openness, because as you deform, you reach the cusp, and like the theory behaves well if you just like for like finitely generated groups, if you assume that all the cusp or all the like boundary component have some fixed point, all the peripheral elements have some fixed point in the flag space, then you have connected component. You disconnect the character variety and you get connected.
Yes? If the boundary of gamma is not connected, doesn't step 2 run into a problem?
Yeah, I mean this argument is more complicated, but it is still true. Like that's like this approach here we only did it for closed surfaces, but you can, I mean like the approach that I did not explain to you of the Guichard-Labourie-Wienhard paper that has like contraction on diamonds, that's based on contraction on diamonds, that works without the assumption of having really full circle. Yeah?
What do you mean when you say that you can deform a funnel into a cusp?
Yeah, I mean, so like the idea here is that like if I look at let me explain that to you later. Let me give some ideas of this proof that, yeah. So like I wanted to say something about towards the proof of theorem. So what I was saying is that we know that CR omega, this cross ratio on the flag space that depending on omega, that was coming from a representation with omega as fundamental group and the projective cross ratio there, has this thing, gamma plus, gamma minus, x, gamma x was equal to that quantity there. This is always omega alpha of lambda of rho of gamma. So this was what we were discussing yesterday, and I missed the 2 yesterday, sorry. Like actually, to be correct, here should be this, omega alpha of lambda of rho of gamma plus omega alpha of lambda of rho of gamma inverse. This was a mistake I made yesterday. That's not so important if you like, I mean, it's important, but sorry. So like the periods of this cross ratio, even if the cross ratio is non-symmetric, it always gets symmetrized. And so this we know how to read that quantity, but the quantity I care about, the quantity on the left with this alpha, that was what was important to be able to control alpha. We don't know how to control it. Like there is, like we don't know what's the, like this cross ratio doesn't see the gap between 2 eigenvalues, only see products of eigenvalues. And to do this, I mean to control that, we introduce photons. Let me find what I. And these are an important object that I was hoping at this point of having more Lie theory to tell you more, but so to read E to the alpha of lambda of rho of beta, we study photons and photon projections. And these are interesting objects that also appeared in Blandin-Gallier, who's their thesis, for very different purposes. And you should go and ask her, because I think it's a great result. And you should like chat with her about it. I don't have time to tell you what this is, but and the idea is that in the flag manifold f theta, so like let me draw this as a cartoon. We can think of this to be f1 p minus 1 of RPQ, the flags of isotropic subspaces, for example. And the point is that in these flag manifolds, for any alpha in theta, so this is f theta, there exists a distinguished family of RP1s, which are these that we call photons, that behave well with the cross ratio. So this is phi alpha, this is a photon. And if this is a point x in my flag manifold, this phi alpha is really a projective line that lands in the bad set that I was discussing. Like it's a line that's as badly transverse to x as it gets, not being x. So this can be, and this depends on alpha. Okay? So let me give you maybe an example. So this is a general theory. Like this works well whenever the root space of alpha is one-dimensional. This determines an RP1, this root space. I don't have the Lie theory necessary to tell you how this works in general, but let me tell you in SOPQ maybe. So in SOPQ, if we get, like we always look at F1P, the flag space relevant for theta positivity, and then if I choose alpha k, the photon phi alpha k through a point x in the flag manifold of x, which is L1 inside L2 inside LP minus 1, and these are all isotropic subspaces, is the set of points on the form L1 up to LK minus 1, and then M, and then LK plus 1, and then LP minus 1. If this is equal to this, so these things here, if k is smaller than p minus 1, and this is isomorphic to the projective space of Lk plus 1 over Lk minus 1. And if k is equal to p minus 1, then we choose L P isotropic containing LP minus 1, and we set and the photon phi alpha p minus 1 of L is P of LP over LP minus 2.
What's that capital
M? M is anything that I can put here to get a flag. So M is a k-dimensional subspace. So like I started from this thing, and I only changed the k piece by putting anything that I could put. So to be, for this to be in the flag space, whatever there is, I need this M to be inside LK plus 1. This forces it to be isotropic, and need to contain LK minus 1. So this is why it's canonically identified with the projective space of LK plus 1 over LK minus 1. So this is an RP1 because this is like, it's a R2.
Okay.
And this fits naturally in the flag manifold. And these are all very non-transverse to my base point because I have lots of things in common, right? So it's really bad. Like it's because in SO2P, these are really the photons. Like in SO2P, the flag space that we care about is this. So this is Francois Labourie's terminology. I'm not sure if it's good or not. But if I look at SO2Q, then the photons are really the lines in this. Like in SO2Q, I have a metric of signature 1, Q minus 1. And these are really the lines in the light cone that are photons for that Minkowski space. And actually, this is what it is in this, like in this K space. I really see this picture, and these are really like light line in a cone in some Einstein universe. Okay. For some more Lie theory, if one knows Lie theory, you can do this generally for any flag space. You identify the tangent space at X with the unipotent radical, and you take the root space for alpha, that's one-dimensional, and this is tangent to a unique manifold that's isomorphic to RP1. And you have nice group theoretic properties. I don't want to write this. You can read it in the paper. Yeah?
So when you say that you have a distinguished family of RP1s, what you mean is through every point of the flag space there is a unique photon?
No.
Okay.
No, there are more. There is a family of photons, but this is G equivariant, this family. So by distinguished family of photons, I mean that there exists a distinguished family of RP1s where the group acts. And actually in this case, for given any point and any index up to P, I have only one photon, which is this guy here. But in the last bit, I need to choose this guy. And this is really this picture, right? So like this LP is really like one line in this, like if I think of this as LP minus 2 perp over LP minus 2, this is R2 and R2n for some n that you can compute easily. Like I had this point L1 up to LP minus 1. I forget LP minus 1. I take this guy, and I can consider this space of the signature 2n, which is the quotient of the orthogonal of the last guy that I had, modulo the last guy. There I have a metric of signature 2, n or whatever n, and it's a combination of p and q that I don't want to mess up on the board. And then in that case, this is LP minus 1, my base point. And choosing a photon is the same as choosing this LP, which is the same as choosing a photon in that picture. Like in this, choosing one line in that cone. And any line is equally nice. So I don't have a G equivariant way of choosing one of those lines. the same picture works for any theta positive group. More questions or comments? So in a slightly different setting, so especially, so like Blandin was using these photons in studying actions on flag manifolds that are also compact symmetric spaces, right? And domains of discontinuity in there, and like doing Hilbert geometries in there. And so you should talk with her. Like you have 1 more week and a half, I think she's going to be here. Just talk with her. Yeah? Okay, so I have these photons, I have this family of RP1. And something that I like about RP1 is that I have the standard cross ratio that I were starting from in discussing cross ratios yesterday. And I was telling you that the standard cross ratio on RP1 has very nice symmetries, has more symmetries than this flag cross ratio that I have here. And this is what we're going to use. And like something that we proved and that also Blandin proved, let me see where I write this statement correctly. Okay, so like there are 2 properties of photons that are important. So one proposition. Okay, and observe that if now, so this theory you can do it for all flag spaces where the root spaces are one-dimensional. Otherwise, you get spheres naturally. But in this, so the observation is that if f theta has a positive structure, as diamonds, then photons belong to the boundary of diamonds. So this is my point x. This is a diamond determined by x and another guy. And my photon really is some projective line in this boundary. This boundary is a very complicated space in general, but you should think of this photon as a line in there. And the proposition is that for any phi, so this is isomorphic to RP1, is a subset of f theta, then I can define a big set O phi, which is the points in f theta such that there exists a point x in the photon. Oh, maybe I should call this z. In the photon with z transverse to y. So now the picture here is that I have my phi, and this is maybe this phi is a photon through a point x, and I want to look at the points such that the points y in my photon, y in f theta, sorry, y in f theta, such that there exists a point z in the photon, so that these 2 are in general position. So that's, like, for example, lots of points are in general position with at least some. But a point in the photon is never transfers to any other point in the photon. So this is not the full flag manifold. So this is a big open set, I mean, open and dense in f theta. And if phi is in x and d x y x b is in my family of diamonds, then d is in O phi. This is not hard to check, but I didn't give you enough Lie theory to check this correctly. So I haven't finished the proposition. The proposition is for any photon phi, defining O phi in this way, the set of points in the flag manifold such that there exists one point transverse to them in the photon. Then there is an equivariant projection from O phi to phi. Given by, I take a point x, y in O phi, and I associate to it the w, which is uniquely determined by w is not transverse to y. Not transverse to y. So like the idea here is that I had this, the picture was there. I have y, it's transverse to at least one point in the photon. Then what can I do? I can look at all the points in the flag manifolds that are non-transverse to y, this bad codimension 1 set. And the statement is that these bad codimension 1 set intersect the photon in exactly one point, p phi of y. Okay, my time is running up.
You have 7 minutes. 7.
Okay, what? Equivariant for what? I mean, like, so this is equivariant for the G action on the flag space and the photon. So that's like, it's a natural projection.
Sorry, so W here is p phi 1?
Yeah. Yeah, this was the, yeah, sorry. So this is p phi from O5 to phi that intersects. Yeah. But with this point, that's a unique point determined like this. There's a natural projection this way. Okay, let's try to bring this home in 7 minutes. Okay, and we have some properties. Where is my thing? Let me try to summarize the property. So, like, there are some features of compatibility of this photon projection with the cross ratio. So the first one is that for any photon phi and for any y, z in the open set, such that p phi of y is equal to p phi of z, then, and for any x and w in phi minus p phi of y, we have that the cross ratio of x, w, y, z is equal to 1. So I add my photon. So I had 2 points, x and w in the photon, and I choose any other 2 point, y and z outside, so that their photon projection is the same. So p phi of y equal p phi of z. Then, if I look at the cross ratio on the flag manifold of these 4 points, then it's 1, which is the 0, because it's a multiplicative cross ratio. So this is the first property that's important. And the second property is that is a theorem that we prove. If theta positivity then for any gamma in G, theta loxodromic, and x in f theta, such that gamma plus gamma minus x, gamma x is positive, then e to the alpha of lambda of gamma is bigger or equal than the minimum over the photon through gamma minus of the cross ratio of p phi of gamma plus gamma minus x and gamma x. So of course I don't have enough space for a picture, but what this theorem, let me draw the picture there. What this theorem is telling me is that if the family has diamonds, and I choose a gamma in G, for example, in row of gamma, and I choose this point here is gamma minus. This is a point x. Here is a point gamma x, and here is the point gamma plus. So I have a diamond through gamma minus and gamma plus that contains x and gamma x. What I'm saying is that the infimum over all photons phi that contain gamma minus of the cross ratio between these 4 points and that point here, so this is p phi of gamma plus, so then this is bounding e to the alpha of lambda of gamma. So let me finish by maybe just let me finish by just drawing one picture. So like with these we can prove the color lemma with this inequality between eigenvalues. So let me just sketch a proof. And what we need to show is that 1 over e to the alpha of gamma plus 1 over e to the omega of beta is, so these are all big, so this is more than 1. So this is an algebraic reformulation of that. So that, so like you can check that start, like apart from the fact that I'm dropping lambda and rho for the interest of time and of readability, this is what I need to check. This is an algebraic reformulation of that. And now we draw one picture, which is omega. So like this is the axis of gamma. This is the axis of beta. This is a picture in H2 that records the orientation in the boundary. And now you can check using hyperbolic geometry that I'll have this configuration here always. Since I have a hyperbolic structure, I know that gamma of beta plus, so this is gamma plus, and this is gamma minus, this is beta plus, and this is beta minus. You can check that gamma of beta plus is on that side of beta of gamma plus. So that this is the ordering in the circle. This is like, I mean, if they are simple as in the picture, it's very easy to persuade yourself, and in general you prove it by finding suitable covers or doing your hyperbolic geometry, that they cannot cross these two geodesics. Because the group is discrete, is acting discretely. Once you have this picture, basically now I think of this in the flag manifold, and I put photons in here. So this is a photon that I'm going to use, and I will have the projection on these photons of beta plus and gamma of beta plus, and the gamma plus, that's maybe down here. These reads the root, and the cross ratio of other 4 points read the weight. And so you just I won't have time to do this trick in -2 minutes, but the idea is that you start from this picture and you use positivity of the cross ratio to like for 1, you care about these 4 points, beta plus and gamma beta plus, and their projection in here. And for the other cross ratio, we care about for the root you care about these 4 points here, and for the weight you care about these 4 points here. And then it becomes a trick that I can like write on the board, but it's not going to be very useful, into swapping these points and using crucially the extra symmetry of this cross ratio that allows me to do a half turn, essentially. So that using the fact that this is an RP1 and the cross ratio restricted on this RP1 has some extra symmetry that the global cross ratio did not have. So like this is not enough to fill up the proof, but you can read the proof in our paper. It's a couple of pages of plays with the cross ratio and positivity, but I hope this gives you a little, at least the idea of how this goes and what are the key ingredients that work. And I think that like these photons are very important, and maybe you'll find applications of this also in other geometric setting. And I think I'll finish here, and thank you for your attention.